The North American Aviation XB-70 Valkyrie was the prototype of the B-70 nuclear-armed, deep-penetration strategic bomber for the Strategic Air Command of the U.S. Air Force. In the 1950s, the North American Aviation Company designed the Valkyrie bomber as a large, six-engine aircraft capable of reaching Mach 3+ while flying at 70,000 feet, which velocity and altitude capabilities would allow the evasion of interceptor aircraft, then the only effective weapon against bomber aircraft. In 1961, improved, high-altitude surface-to-air missiles, the U.S. Air Force's doctrinal change to low-level penetration bombing, the large development costs of the B-70 program, and the introduction of intercontinental ballistic missiles to the U.S. nuclear arsenal, led to the cancellation of the B-70 program. As such, two prototype aircraft were built, and designated XB-70A. These aircraft were used for supersonic test flights during 1964-69. In 1966, one prototype crashed after colliding in midair with a smaller jet aircraft. The remaining Valkyrie bomber is in the National Museum of the United States Air Force, in Ohio. Development, background. As an offshoot of Boeing's MX-21 manned boost glide bomber project, Boeing partnered with RAND Corporation in January 1954 to explore what sort of aircraft would be needed to deliver the various nuclear weapons then under development. Providing for a long range and high payload were obvious requirements, but they also concluded that after release of nuclear bombs the bomber would need supersonic speed to escape the critical blast radius. The aircraft also had to be large to carry a reasonable bomb load and a high fuel load for the unrefueled range required from the continental United States to the Soviet Union. For some time the aviation industry had been examining this problem. From the mid-1940s, there was much interest in using nuclear-powered aircraft in the bomber role. In a conventional jet engine, thrust is provided by accelerating air, which is accomplished by heating it with burning jet fuel. In a nuclear engine, heat is supplied by a reactor, although a small amount of jet fuel was carried for use during high-power portions of flight takeoff and high-speed dashes. Another possibility was the use of boron-enriched zip fuels, which improved the energy density of the fuel by about 40%, and could be used in versions of existing jet engine designs. Zip fuels appeared to offer sufficient performance improvement to produce a strategic bomber with supersonic speed. The U.S. Air Force followed these developments closely, and in 1955 issued General Operational Requirement No. 38 for a new bomber with the payload and intercontinental range of the B-52 and the Mach 2 top speed of the Convair B-58 Hustler. The new bomber was expected to enter service in 1963. Both nuclear and conventional designs would be considered. The nuclear-powered bomber was placed under Weapons System 125A, and pursued simultaneously with the jet-powered version, Weapons System 110A. The USAF Air Research and Development Command's requirement for WS-110A asked for a chemical fuel bomber with Mach 0.9 cruising speed and maximum possible speed during a 1,000 nautical miles in trans and exit from the target. The requirement also called for a 50,000 pound payload and a combat radius of 4,000 nautical miles. The Air Force formed similar requirements for a WS-110L intercontinental reconnaissance system in 1955, but this was later cancelled in 1958 due to better options. In July 1955 6 contractors were selected to bid on WS-110A studies. Boeing and North American Aviation submitted proposals, and on November 8, 1955 were awarded contracts for Phase 1 development. In mid-1956, initial designs were presented by the two companies. Zip fuel was to be used in the afterburners to improve range by 10 to 15% over conventional fuel. Both designs featured huge wingtip fuel tanks that could be jettisoned when their fuel was depleted before a supersonic dash to the target. The tanks also included the outer portions of the wing, which would also be jettisoned to produce a smaller wing planform suitable for supersonic speeds. The two designs had takeoff weights of approximately 750,000 pounds with large fuel loads. The Air Force evaluated the designs, and in September 1956 deemed them too large and complicated for operations. The USAF ended Phase 1 development in October 1956 and instructed the two contractors to continue design studies. Curtis LeMay was dismissive, declaiming, "This is not an airplane, it's a three-ship formation." New designs. During the period that the original proposals were being studied, advances in supersonic flight were proceeding rapidly. The long-thin Delta was establishing itself as a preferred platform for supersonic flight, replacing earlier designs like the swept wing and compound sweeper seen on designs like the Lockheed F-104 Starfighter. Engines able to cope with higher temperatures and widely varying inlet air speeds were also under design, allowing for sustained supersonic speeds. By March 1957, engine development and wind tunnel testing had progressed such that the potential for all supersonic flight appeared feasible. The cruise and dash approach that had resulted in huge designs was no longer needed. The project decided that the aircraft would fly at speeds up to Mach 3 for the entire mission, instead of a combination of subsonic cruise and supersonic dash of the aircraft designs in the previous year. Zip fuel was to be burned in the engines afterburner to increase range. Both North American and Boeing returned new designs with very long fuselages and large delta wings. They differed primarily in engine layout. The NAA design arranged its 6 engines in a semicircular duct under the rear fuselage, while the Boeing design used separate podded engines located individually on pylons below the wing. North American had scoured the literature to find any additional advantage. This led them to an obscure report by two NACA wind tunnel experts who wrote a report in 1956 entitled Aircraft Configurations Developing High Lift-Drag Ratios at High Supersonic Speeds. Known today as compression lift, the idea was to use the shock wave generated off the nose or other sharp points on the aircraft as a source of high-pressure air. By carefully positioning the wing in relation to the shock's high pressure could be captured on the bottom of the wing and generate additional lift. To take maximum advantage of this effect, they redesigned the underside of the aircraft to feature a large triangular intake area far forward of the engines, better positioning the shock in relation to the wing. North American improved on the basic concept by adding a set of drooping wingtip panels that were lowered at high speed. This helped trap the shock wave under the wing between the downturned wing tips, and also added more vertical surface to the aircraft to improve directional stability at high speeds. NAA's solution had an additional advantage, as it decreased the surface area of the rear of the wing when the panels were moved into their high-speed position. This helped offset the rearward shift of the center of pressure, or average lift point, with increasing speeds. Under normal conditions this caused an increasing nose-down trim, which had to be offset by moving the control surfaces, increasing drag. When the wing tips were drooped, the surface area at the rear of the wings was lowered, moving the lift forward and counteracting this effect, reducing the need for control inputs. The buildup of heat due to skin friction during sustained supersonic flight had to be addressed. During a Mach 3 cruise the aircraft would reach an average of 450 AA°F, with leading edges reaching 630 AA°F, and up to 1000 AA°F in engine compartments. NAA proposed building their design out of sandwich panels, with each panel consisting of two thin sheets of stainless steel brazed to opposite faces of a honeycomb-shaped foil core. Expensive titanium would be used only in high-temperature areas like the leading edge of the horizontal stabilizer, and the nose. For cooling the interior, the XB-70 pumped fuel en route to the engines through heat exchangers. On 30 August 1957, the Air Force decided that enough data was available on the NAA and Boeing designs that a competition could begin. On 18 September, the Air Force issued operational requirements which called for a cruising speed of Mach 3.0 to 3.2, an over-target altitude of 70,000 to 75,000 ft, a range of up to 10,500 mi, and a gross weight not to exceed 490,000 lb. The aircraft would have to use the hangars, runways and handling procedures used by the B-52. On 23 December 1957, the North American proposal was declared the winner of the competition, and on 24 January 1958, a contract was issued for Phase 1 development. In February 1958, the proposed bomber was designated B-70, with the prototypes receiving the X-experimental prototype designation. The name Valkyrie was the winning submission in early 1958, selected from 20,000 entries in a USAF-named the B-70 contest. The Air Force approved an 18-month program acceleration in March in 1958 that rescheduled the first flight to December 1961. But in late 1958 the service announced that this acceleration would not be possible due to lack of funding. In December 1958, a Phase 2 contract was issued. The mock-up of the B-70 was reviewed by the Air Force in March 1959. Provisions for air-to-surface missiles and external fuel tanks were requested afterward. At the same time North American was developing the F-108 supersonic interceptor. To reduce program costs, the F-108 would share two of the engines, the escape capsule, and some smaller systems with the B-70. In early 1960, North American and the USAF released the first drawing of the XB-70 to the public. The missile problem. The B-70 was planned to use a high-speed, high-altitude bombing approach that followed a trend of bombers flying progressively faster and higher since the start of manned bomber use. Anti-aircraft artillery with the ability to reach jet bomber altitudes of 50,000 aft and above was extremely expensive, and had almost no chance of a hit as the aircraft quickly flew out of range. Interceptor aircraft were the only effective anti-bomber weapons by the early 1950s, but high altitudes were an issue for them as well. Soviet interceptors during the late 1950s could not intercept the higher altitude U-2 reconnaissance aircraft. It was later discovered that flying faster made radar detection much more difficult due to an effect known as the blip-to-scan ratio, and any reduction in tracking efficiency would further interfere with the operation and guidance of fighters. The introduction of the first effective anti-aircraft missiles by the late 1950s had seriously upset this equation. Missiles could stand ready for immediate launch directly at the bombers, eliminating operational delays like the time needed to get the pilot into the cockpit of a fighter. Guidance did not require wide-area tracking or calculation of an intercept course. A simple comparison of the time needed to fly to the altitude of the target returned the required lead. Missiles also had greater altitude capability than any aircraft, and improving this to adapt to new aircraft was a low-cost development path. The U.S. was aware of Soviet work in the field, and had reduced the expected operational lifetime of the U-2, knowing that it would become vulnerable to these missiles as they were improved. This eventuality came to pass in the 1960 downing of the U-2 flown by Gary Powers. Faced with this problem, military doctrine had already started shifting away from high-altitude supersonic bombing toward low-altitude penetration. As radar operates on the line of sight, aircraft could dramatically shorten detection distances by flying close to the Earth and hiding behind terrain. Missile sites spaced to overlap in range when attacking bombers at high altitudes would leave large gaps between their coverage for bombers flying at lower levels. With an appropriate map of the missile sites, the bombers could fly between and around the defenses. Additionally, early missiles generally flew unguided for a period of time before the radar systems were able to track the missile and start sending it guidance signals. With the SA-2 guideline missile, this minimum altitude was roughly 2,000 ft. Flying below this would make the bomber effectively invulnerable to the missiles, even if they happened to fly into range. Flying at low level provided protection against fighters as well. Radars of the era did not have the ability to look down. If the radar were aimed down to detect targets at a lower altitude, the reflection of the ground would overwhelm the signal returned from a target. An interceptor flying at normal altitudes would be effectively blind to bombers below it. The interceptor could descend to lower altitudes to increase the amount of visible sky above it, but doing so would limit its radar range in the same way as the missile sites, as well as greatly increasing fuel use and thus reducing mission time. The Soviet Union would not introduce an interceptor with look-down capability until 1972 with the Hilark radar, and even this model had very limited capability. Strategic Air Command found itself in an uncomfortable position. Bombers had been tuned for efficiency at high speeds and altitudes, performance that had been purchased at great cost in both engineering and financial terms. Before the B-70 was to replace the B-52 inches the long-range role, SAC had introduced the Convair B-58 Hustler to replace the Boeing B-47 Stratojet in the medium-range role. The Hustler was expensive to develop and purchase, and required enormous amounts of fuel and maintenance in comparison to the B-47. It was estimated that it cost 3 times as much to operate as the much larger and longer-ranged B-52. The B-70, designed for even higher speeds, altitudes and range than the B-58, suffered even more in relative terms. At high altitudes the B-70 was as much as 4 times faster than the B-52, but at low altitudes it was limited to only Mach 0.95, only modestly higher than the B-52 at the same altitudes. It also had a smaller bomb load and shorter range. Its only major advantage would be its ability to use high speed in areas without missile cover, especially on the long journey from the USA to USSR. The value was limited. The USAF's doctrine stressed that the primary reason for maintaining the bomber force in an era of ICBMs was that the bombers could remain in the air at long ranges from their bases and were thus immune to sneak attack. In this case, the higher speed would be used for only a short period of time between the staging areas and the Soviet coastline. Adding to the problems, the ZIP fuel program was cancelled in 1959. After burning, the fuel turned into liquids and solids that increased wear on moving turbine engine components. Although the B-70 was intended to use ZIP only in the afterburners, and thus avoid this problem, the enormous cost of the ZIP program for such limited gains led to its cancellation. This by itself was not a fatal problem, however, as newly developed high-energy fuels like JP6 were available to make up some of the difference. Most of the range lost in the change from ZIP fuel was restored by filling one of the 2 bomb bays with a fuel tank. Also, the F-108 program was cancelled in September 1959, which ended the shared development that benefited the B-70 program. Downsizing, upswing, cancellation. At 2 secret meetings on 16 and 18 November 1959, the chairman of the Joint Chiefs of Staff, Air Force General Twining, recommended the Air Force's plan for the B-70 to reconnoiter and strike rail-mobile Soviet ICBMs, but the Chief of Staff of the Air Force, General White, admitted the Soviets would be able to hit the B-70 with rockets, and requested the B-70 be downgraded to a bare minimum research and development program at $200 million for fiscal year 1960. President Eisenhower responded that the reconnaissance and strike mission was crazy since the nuclear mission was to attack known production and military complexes, and emphasized he saw no need for the B-70 since the ICBM is a cheaper, more effective way of doing the same thing. Eisenhower also identified that the B-70 would not be in manufacturing until 8 to 10 years from now, and said he thought we were talking about bows and arrows at a time of gunpowder when we spoke of bombers in the missile age. In December 1959 the Air Force announced the B-70 project would be cut to a single prototype, and most of the planned B-70 subsystems would no longer be developed. Then interest increased due to the politics of presidential campaign of 1960. A central plank of John F. Kennedy's campaign was that Eisenhower and the Republicans were weak on defense, and pointed to the B-70 as an example. He told a San Diego audience near NAA facilities, "I endorse wholeheartedly the B-70 manned aircraft." Kennedy also made similar campaign claims regarding other aircraft. Near the Seattle Boeing plant he affirmed the need for B-52s, and in Fort Worth he praised the B-58. The Air Force changed the program to full weapon development and awarded a contract for an XB-70 prototype and 11 YB-70s in August 1960. In November 1960, the B-70 program received a $265 a million appropriation from Congress for FY 1961. Nixon, trailing in his home state of California, also publicly endorsed the B-70, and on October 30 Eisenhower helped the Republican campaign with a pledge of an additional $155 a million for the B-70 development program. On taking office in January 1961, Kennedy was informed that the missile gap was an illusion. On 28 March 1961, after $800 a million had been spent on the B-70 program, Kennedy canceled the project as unnecessary and economically unjustifiable, because it stood little chance of penetrating enemy defenses successfully. Instead, Kennedy recommended the B-70 program be carried forward essentially to explore the problem of flying at 3 times the speed of sound with an airframe potentially useful as a bomber. After Congress approved $290 million of B-70 add-on funds to the President's May 12, 1960 modified FY 1961 budget, the administration decided on a planned utilization of only $100 million of these funds. The Department of Defense subsequently presented data to Congress that the B-70 would add little performance for the high cost. However, after becoming the new Air Force Chief of Staff in July 1961, Curtis LeMay increased his B-70 advocacy, including interviews for August Reader's Digest and November Aviation Week articles, and allowing a 25 February General Electric tour at which the press was provided artist conceptions of, and other info about, the B-70. Congress had also continued B-70 appropriations in an effort to resurrect bomber development. After Secretary of Defense Robert McNamara explained again to the House Armed Services Committee on 24 January 1962 that the B-70 was unjustifiable, LeMay subsequently argued for the B-70 to both the House and Senate committees and was chastised by McNamara on 1 March. By 7 March 1962, the House with 21 members having B-70 work in their districts had written an appropriations bill to direct by law the executive branch to use all of the nearly $500 million appropriated for the RS-70. McNamara was unsuccessful with an address to the HASC on 14 March, but a 19 March 1962 11th-hour White House Rose Garden agreement between Kennedy and HASC Chairman Carl Vinson retracted the bill's language and the bomber remained cancelled. Experimental aircraft, the XB-70s were intended to be used for the advanced study of aerodynamics, propulsion, and other subjects related to large supersonic transports. The crew was reduced to only the 2 pilots, as a navigator and a bombardier were not needed for this research role. The production order was reduced to 3 prototypes in March 1961 with the 3rd aircraft to incorporate improvements from the previous prototype. The order was later reduced to 2 experimental XB-70 as, named Air Vehicle 1 and 2. XB-70 No. 1 was completed on May 7, 1964, and rolled out on May 11, 1964 at Palmdale, California. One report stated nothing like it existed anywhere. AV-2 was completed on October 15, 1964. The manufacture of the 3rd prototype was cancelled in July 1964 before completion. The first XB-70 carried out her maiden flight in September 1964 and many more test flights followed. The data from the XB-70 test flights and aerospace materials development were used in the later B-1 bomber program, the American Supersonic Transport Program, and via espionage, the Soviet Union's Tupolev Tu-144 SST program. The development of the Lockheed U-2 and the SR-71 Blackbird reconnaissance aircraft, as well as the XB-70, prompted Soviet aerospace engineers to design and develop their high-altitude and high-speed MiG-25 interceptor. Design: the Valkyrie was designed to be a high-altitude Mach 3 bomber with 6 engines. Harrison Storms shaped the aircraft with a canard surface and a delta wing, which was built largely of stainless steel, sandwiched honeycomb panels, and titanium. The XB-70 was designed to use supersonic technologies developed for the Mach 3 Navajo, as well as a modified form of the SM-64 Navajo's all-inertial guidance system. The XB-70 used compression lift, which was generated from a prominent wedge at the center of the engine inlets that created a shock wave below the aircraft. The wing included inboard camber to more effectively use the higher pressure field behind the strong shock wave. The compression lift increased the lift by 5%. Unique among aircraft of its size, the outer portions of the wings were hinged, and could be pivoted downward by up to 65 degrees. This increased the aircraft's directional stability at supersonic speeds, shifted the center of lift to a more favorable position at high speeds, and strengthened the compression lift effect. With the wingtips drooped downwards, the compression lift shock wave would be further trapped under the wings. The XB-70 was equipped with 6 General Electric YJ93 GE3 turbojet engines, designed to use JP6 jet fuel. The engine was stated to be in the 30,000 pound class, but actually produced 28,000 pound force with afterburner and 19,900 pound force without afterburner. The Valkyrie used fuel for cooling. It was pumped through heat exchangers before reaching the engines. To reduce the likelihood of hot ignition, nitrogen was injected into the JP6 during refueling, and the fuel pressurization and inerting system vaporized a 700 lb supply of liquid nitrogen to fill the fuel tank vent space and maintain tank pressure. Operational history. The XB-70's maiden flight was on September 21, 1964. In the first flight test, between Palmdale and Edwards AFB, shortly after takeoff one engine had to be shut down, and an undercarriage malfunction warning meant that the flight was flown with the undercarriage down as precaution, limiting speed to 390 mph, about half that planned. On landing, the rear wheels of the portside main gear locked, the tires ruptured, and a fire started. The Valkyrie first became supersonic on the third test flight on October 12, 1964, and flew above Mach 1 for 40 minutes during the following flight on October 24. The wingtips were also lowered partially in this flight. XB-70 No. 1 surpassed Mach 3 on October 14, 1965 by reaching Mach 3.02 at 70,000 aft. The first aircraft was found to suffer from weaknesses in the honeycomb panels, primarily due to inexperience with fabrication and quality control of this new material. On 2 occasions, honeycomb panels failed and were torn off during supersonic flight, necessitating a Mach 2.5 limit being placed on the aircraft. The deficiencies discovered on AV-1 were almost completely solved on the second XB-70, which first flew on July 17, 1965. On 3 January 1966, XB-70 No. 2 attained a speed of Mach 3.05 while flying at 72,000 aft. AV-2 reached a top speed of Mach 3.08 and maintained it for 20 minutes on 12 April 1966. On May 19, 1966, AV-2 reached Mach 3.06 and flew at Mach 3 for 32 minutes, covering 2,400 mi in 91 minutes of total flight. A joint NASA-USAF research program was conducted from 3 November 1966 to 31 January 1967 for measuring the intensity and signature of sonic booms for the National Sonic Boom Program. Testing was planned to cover a range of sonic boom overpressures on the ground similar to but higher than the proposed American SST. In 1966, AV-2 was selected for the program and was outfitted with test sensors. It flew the first sonic boom test on June 6, 1966, obtaining a speed of Mach 3.05 at 72,000 aft. 2 days later, AV-2 crashed following a mid-air collision with an F-104 while flying in a multi-aircraft formation. Sonic boom and later testing continued with XB-70A No. 1. The second flight research program investigated control of structural dynamics from 25 April 1967 through the XB-70's last flight in 1969. At high altitude and high speed, the XB-70 experienced unwanted changes in altitude. NASA testing from June 1968 included 2 small vanes on the nose of AV-1 for measuring the response of the aircraft's stability augmentation system. AV-1 flew a total of 83 flights. The XB-70's last supersonic flight took place on December 17, 1968. On 4 February 1969, AV-1 took its final flight to Wright-Patterson Air Force Base for museum display. Flight data was collected on this subsonic trip. North American Rockwell completed a 4-volume report on the B-70 that was published by NASA in April 1972. Variants: XB-70A, prototype of B-70. 2 were built. AV-1, NAA model number NA278, USAF SN 62-0001, completed 83 flights spanning 160 hours and 16 minutes. AV-2, NAA model number NA278, USAF SN62-0207, flew 46 times over 92 hours and 22 minutes, before it crashed in June 1966. XB-70B, AV3, NAA model number NA274, USAF SN62-0208, was originally to be the first YB-70A in March 1961. This advanced prototype was cancelled during early manufacture. YB-70, planned pre-production version with improvements based on XB-70s. B-70A, planned bomber production version of Valkyrie. A fleet of up to 65 operational bombers was planned. RS-70, proposed reconnaissance strike version with a crew of 4 and in-flight refueling capability. Incidents and accidents. Incidents. On May 7, 1965, the dividers separating the left and right halves of XB-70A AV-1's engine inlet broke off in flight and were ingested by all 6 engines, damaging them beyond repair. On October 14, 1965, AV-1 surpassed Mach 3, but heat and stress damaged the honeycomb panels, leaving 2 ft of the leading edge of the left wing missing. The first aircraft was limited to Mach 2.5 afterwards. Midair collision. On June 8, 1966, XB-70A No. 2 was in close formation with 4 other aircraft for a photo shoot at the behest of General Electric, manufacturer of the engines of all 5 aircraft. After the completion of the photo shoot, the F-104 drifted into contact with the XB-70's right wing, flipped over and rolled inverted over the top of the Valkyrie, striking the vertical stabilizers and left wing of the bomber. The F-104 exploded, destroying the Valkyrie's rudders and damaging its left wing. With the loss of both rudders and damage to the wings, the Valkyrie entered an uncontrollable spin and crashed into the ground north of Barstow, California. NASA Chief Test Pilot Joe Walker and Carl Cross were killed. Al White ejected, sustaining serious injuries, including one arm crushed by the closing clamshell-like escape capsule moments prior to ejection. The USAF summary report of the accident investigation stated that, given the position of the F-104 relative to the XB-70, the F-104 pilot would not have been able to see the XB-70's wing, except by uncomfortably looking back over his left shoulder. The report said that Walker, piloting the F-104, likely maintained his position by looking at the fuselage of the XB-70, forward of his position. The F-104 was estimated to be 70 ft to the side of, and 10 ft below, the fuselage of the XB-70. The report concluded that from this position, without appropriate sight cues, Walker was unable to properly perceive his motion relative to the Valkyrie, leading to his aircraft drifting into contact with the XB-70's wing. The accident investigation also pointed to the wake vortex off the XB-70's right wing tip as the reason for the F-104's sudden rollover and into the bomber. Aircraft on display. Valkyrie Avenue 1 is on display at the National Museum of the United States Air Force at Wright-Patterson AFB near Dayton, Ohio. The aircraft was flown to the museum on 4 February 1969, following the conclusion of the XB-70 testing program. Over the years the Valkyrie became the museum's signature aircraft, appearing on museum letterhead, and even appearing as the chief design feature for the museum's restaurant, the Valkyrie Café. As of 2011, the XB-70 was in the museum's research and development hangar where it is displayed alongside other experimental aircraft in the museum's collection. Specifications, data from PACE, USAF XB-70 Fact Sheet B-70 Aircraft Study. General characteristics: crew, 2, length, 189 feet 0 inches, wingspan, 105 feet 0 in, height, 30 feet 0 in, wing area, 6,297 FTA squared, airfoil, hexagonal. 0.30 hex modified root, 0.70 hex modified tip, empty weight, 253,600 pounds, loaded weight, 534,700 pounds, max takeoff weight, 542,000 pounds, power plant, SIGSA, General Electric YJ93GE3 afterburning turbojet, dry thrust. 19,900-pound forces each, thrust with afterburner, 28,800-pound forces each. Internal fuel capacity, 300,000 pounds or 46,745 US gallons. Performance, maximum speed, Mach 3.1, cruise speed, Mach 3.0, range, 3,725 mi on combat mission, service ceiling, 77,350 feet, wing loading, 84.93 pounds FTA squared, lift to drag, about 6 at Mach 2, thrust weight, 0.314, see also. Aircraft in fiction, XB-70 Valkyrie, Pi Wacket, related development, North American XF-108 Rapier, aircraft of comparable role, configuration and era, Sukhoi T-4, AVO 730, related lists, list of bomber aircraft, list of military aircraft of the United States, references, notes. Citations. Bibliography. External links, Pike, Ian, B-70 The State-of-the-Art Improver Part 1, Flight International, 1055 Euro 1062 Pike, Ian, B-70 The State-of-the-Art Improver Part 2, Flight International, 18 Euro 24 North American XB-70A, XB-70A construction pages on National Museum of the USAF site, NASA DFRC photos and videos, North American XB-70A Valkyrie presentation 1965 on YouTube.com.